Welcome everyone to this fifth talk in the ONEPAS Thematic Series on the partial differential equations of quantum mechanics. And it's a pleasure to have today Ákos Nagy talking to us about novel solutions in Ginzburg Landau theory. Thank you very much, Ákos.
Thank you so much for the invitation. So today I'm going to talk about two works of mine. One was one that came out of my PhD, and the second one is more recent, and I did the second project with Gonçalo Oliveira. So let me introduce Ginzburg-Landau theory very briefly, first on Euclidean backgrounds, so as a PDE on flat Rn, and then I'll talk a little bit about how it looks like on manifolds, because that's going to be my main playground. So Ginzburg-Landau theory, it comes from physics. It is an effective field theory for superconductivity. It is a partial differential equation on basically two unknowns. One is an n-tuple if you're in n dimensions, which you should think of as the electromagnetic vector potential. And I already want to mention that this is going to be a gauge theory. So there are unphysical degrees of freedom, and to cut out most of them, I'm going to assume that we are in Coulomb gauge. That is, the vector potential is divergence free. But you don't have to worry too much about the gauge part for now. I'm just saying that that's so. There's another degree of, or another unknown in the problem of a phi, which is an order parameter. That's the physical meaning of it. If you think about superconductivity, then the normal phi tells you how superconductive the material at a given point is. That's the physical meaning of it. But mathematically, it's a complex scalar field. Out of these, we will construct further quantities. The first one is the electromagnetic field tensor, which is an antisymmetric matrix, if you wish. For mathematical reasons, it's complex, imaginary, purely imaginary valued, so hence the I there. It's not super important just yet, but otherwise it's this antisymmetric quantity that we call the exterior derivative in geometry. And one thing that you might want to note is that minus of this divergence type quantity of f is essentially the Laplacian of the vector potential, because and at that point we use the Coulomb gauge condition. The second induced field is the kinetic term, which is the gauged gradient of phi. It's not just the regular gradient, it's not just partial A of phi, but also I, again, complex I times A sub A phi is added there. And then you have the gauged Laplacian of phi, which is going to be minus the second derivatives, when, again, derivatives are understood in this gauge version. And again, I want to point out that I was raised as a geometer, so my Laplacians are positive definite formally, so they have this minus sign. I have nothing against the other conventions, it's just high roll. So please remember that every time you see a delta, that it's a minus second derivatives. And the third quantity I have to introduce is the supercurrent that is generated by the vector potential and phi. And this is you complex conjugate it, you multiply it by phi, you get some complex number, or really a complex vector. If you look at all components A, you take the imaginary part of it, and that's it. You multiply by I. And you'll see why this is important in a second. There's two coupling constants in the theory. One is what I will call tau in physics. You can interpret that as the temperature, more or less, and geometrically it's sort of the volume of the underlying space. And there's kappa, which is the original interpretation of kappa is sort of the penetration length per the coherence length. It means that there's a penetration length, how far the electromagnetic field can penetrate into or how fast it can penetrate into the superconductor, and the coherence length is is how fast the phi field decays, and the difference of that class distinguishes different types of superconductors, type 1 and type 2 type superconductors. But mathematically speaking, it's just two positive quantity that will be in our energy density. So our energy density is three terms. The first one is your usual Maxwell density. So that's the norm of the electromagnetic field tensor. The second is the kinetic term, or the gradient square term, and there's a potential term. And the potential term, as you can see, is a quartic potential, and this is your usual double well potential, and kappa and tau are really telling you how this double well potential is shaped. And of course, the Ginzburg-Landau energy is the integral of that over your space. And then if you compute the Euler-Lagrange equation of this energy, then you get what we call the Ginzburg-Landau equations. The first equation is this negative divergence, if you wish, of the electromagnetic tensor equals to the supercurrent. This is why I had to introduce that quantity. And the second equation is that the gauge Laplacian of phi is this cubic quantity, given in terms of phi and kappa and tau. So this is how the gauged, when I say Ginzburg-Landau, I always mean gauge Ginzburg-Landau. This is how this theory looks like on Rn. And of course, you can put it on manifolds, but then there's a couple things you have to be careful with. So I'm going to replace Rn with a Riemannian manifold, and the main change, analytically speaking, is that I want a closed manifold for today's purposes. That means that I want this space to be compact and without boundary. You can think of a sphere, a torus, or a surface of higher genus if you want to be in 2D, but of course it can be a higher dimensional thing as well. And on that, I want the Hermitian line bundle. What it means, if you're unfamiliar with bundles, is basically that instead of just having functions that have complex values, I want to have functions that have complex values that satisfy some extra. One way you can imagine that is if you think about the torus as being a square where the endpoints are identified, then having a Hermitian line bundle amounts to having some sort of periodic boundary conditions on that sphere. And if you have some more complicated manifold, then this Hermitian line bundle would account for those more weirder boundary conditions. But you might as well just think about L being complex numbers. Now the unknowns will become more geometric. Instead of the vector potential, now we have a connection, which is a way to differentiate. So you should think about nabla as together partial A and IA. They're now joined and indistinguishable. And phi, the complex scalar field, is now, as I said, a section of this line bundle. You don't have to overthink that. If you like to think more about just flat, PDEs on flat spaces, you can just have in your mind for now what I said on the previous slide. But if you're more comfortable with line bundles and things like that, then I think it's useful. Now the induced fields are the same as last time on the previous slide, but they have different names now. So the electromagnetic field tensor is called now the curvature of nabla. The kinetic term, we call it now the covariant derivative of phi with respect to nabla. And there's again a supercurrent, which is going to be I times the imaginary part. And this H is the Hermitian inner product on this line bundle. So if you write it out in components, this supercurrent will look exactly the same as it did on the previous slide. And we define the energy functional the exact same way, except now we integrate with respect to the Riemannian volume. The Ginzburg-Landau equations will be very similar, but now I'm writing them down in coordinate-free form. But again, in coordinates, they will look like how they did on the previous slide. So it is just for the more geometrically inclined And now I want to mention something. So if you have a nubla that satisfies that this D star F nubla, so this is kind of like a negative divergence, is 0, and you pair such a nubla with phi equals 0 identically, then that will be immediately a solution. This is because the supercurrent will be 0, so the first equation is satisfied, and in the second equation, both sides are immediately 0. So in this way, you can, of course, generate solutions of Ginzburg-Landau, but these are, in a sense, the trivial solutions. What they correspond to physically is an electromagnetic field, because this D star F equals 0 is Maxwell's equation in a compact form. But there's no superconductivity because phi is everywhere 0. Because of that, we call it a normal phase solution, because the material we're looking at is said to be in a normal phase as opposed to the superconducting phase. My first result that I want to talk about is existence of not just sorts of Ginzburg-Landau equations on these compact backgrounds in dimension 2, but also absolute minimizers. So in this case, X is going to be closed, oriented. Oriented means, you know, we're not in on a Klein bottle or something. So closed oriented surface, and nubla null will be a normal phase solution. So from now on, if you see a null on top of nubla, it just means that it's a solution of Maxwell's equation. Then I want to introduce a quantity that I call lambda 1, because it's going to be the smallest eigenvalue of the corresponding Laplacian. So it's nubla null star nubla null. This is the gauge Laplacian corresponding to this thing. So you can compute this nubla or interpret this lambda 1 two ways. One is through Chern-Weil theory, so geometry, and then it will be 2 pi times the absolute value of what we call the degree of the line bundle. Degree of the line bundle measures how non-trivial your line bundle is, and you have to divide by the area. Or the physical interpretation is that this is the external magnetic field. So you think about your surface to be in a magnetic field that's generated externally that is perpendicularly penetrates the surface, then this is that field. This is obviously physically need to be somewhere in the theory. And so in particular, if you have non-zero flux physically or mathematically, if you have a non-trivial line bundle, then this lambda 1 is a positive quantity. And if you have no flux or lambda is trivial, then this is of course 0. So the first theorem that I proved is that if tau times kappa squared, so that if those two coupling parameters in this combination are strictly bigger than lambda 1, then there are non-trivial, in other words, irreducible solutions of the Ginzburg-Landau equations. And the proof is the following. First, I proved that the Ginzburg-Landau energy is gauged Paley-Smale. What it means is that it's not quite Paley-Smale, just because you have a sequence of configurations with bounded energy such that they're, say the left-hand sides, if you solve for 0 in the Ginzburg-Landau equations, then the left-hand sides are, converging to 0 with some norm. It doesn't necessarily mean that your configurations will converge to a solution because of the gauge symmetry. You can always come up with gauges and mess this up. But once you fix your gauge or allow gauge transformations, those are equivalent viewpoints, then it is a Paley-Smale functional. And if you have a Paley-Smale functional that's bounded from below, and our energy is, of course, always non-negative, then there just has to be a global minima. And then, so that this global minima might as well be a normal phase solution, a trivial solution. And what I'm claiming is that it is not that. The next thing is that you just compute the Hessian at the normal phase solution, and you vary in the direction of a section, but not in the direction of one forms. What you see is that it's going to be an inner L to inner product of this Laplacian minus kappa squared tau. So if the smallest eigenvalue of nabla star nabla is lambda 1 and kappa squared tau is bigger than lambda 1, the normal phase solutions are unstable. So it's, the global minima cannot be that. So the difficulty in this this proof was, of course, part 1. So that the previous one was an existence result. Now I would like to talk about a non-existence result in the same setting. So the setup is the same. You're on a closed oriented surface. Again, think about a sphere, a torus, or a donut with even more holes. And lambda 1 is still this smallest eigenvalue of this Laplacian. Then what I'm claiming is that if tau was too large, bigger than this lambda in the previous theorem, then there were non-trivial solutions. But it didn't say anything. The method didn't say anything about what happens when tau is small. This theorem covers this case. It says that if tau is less than lambda 1 times the minimum of 2 or 1 over kappa squared, then there are definitely no non-trivial solutions. So the only solutions are normal phases. There's no superconductivity. For small tau, there's no superconductivity present. So the proof, again, quotation marks before, because I'm only doing just the idea, is first you compute the Laplacian of Laplacian of tau minus phi squared, and you do a maximum principle, and really that's a minimum principle because you look at a minimum of tau minus phi squared, and you'll see that that has to be positive, so phi is bounded by tau. You combine that with another maximum principle where you compute the Laplacian of the field tensor, the electromagnetic field tensor, or the curvature, any way you want to say it. And if you combine those equations, and I don't want to spell out the details here, you can find it in my paper, of course, but ultimately what you will find is this quantity that's 2 times f plus phi squared is bounded by a constant, and the constant is tau times the maximum of 1 and 2 times kappa squared. So, well, I should mention that part of this idea to use the maximum principle or look at the Laplacians of these quantities in the way I did it is from Taubes' thesis and subsequent paper, although he only used it, this idea for kappa squared equals 1/2, which we'll call the critical coupling. But my observation was that it often works, or it works very nicely with small tweaks in the non-critical situation as well. And ultimately, what you do is you integrate both sides. The integral of phi squared is of course positive, so you can, if you get rid of it, then the inequality will still hold. And the integral of f can be bounded below in terms of lambda 1, even again because of Chern-Weil theory. So I don't want to spell out the details here again. The idea is that after this inequality, we're almost there. We just have to integrate and use Chern-Weil theory. But now, if you recall the theorem from the previous slide, I said if kappa squared tau is bigger than lambda 1, then then there are non-trivial solutions. And here I'm saying that under other hypotheses, there are no non-trivial solutions. And it turns out that the two conditions sharply match when kappa is bigger than the critical kappa, which I forgot to write here, that is, it's 1/√2. So when kappa squared is bigger than 1/2, then the two conditions nicely match up. And you can say this theorem that applies to critically coupled and type 2 coupled superconductors, that in this case, there are non-trivial solutions if and only if, or exactly when tau kappa squared is strictly greater than lambda 1. All right, so what I said so far proves the existence or the lack of minimal solutions. Actually, that's not true. The non-existence result rules out non-minimal irreducible solutions as well. But when there exists non-trivial solution, I couldn't say anything about non-minimal ones. And that was something I originally set out to analyze, because on flat R2, Taubes proved again in his thesis that on flat R2, you cannot have non-minimal or unstable critical points with finite energy in the appropriate sense. So that led me to search for these ever since. But before I tell you what I found, I want to tell you what has been known about solutions on closed manifolds. A lot is known about solutions on Euclidean spaces or compact domains with certain types of boundaries. That's not what I'm thinking right now. I'm thinking about closed manifolds, so compact and without boundary. Well, one of the nicest, geometrically speaking, nicest situation is when you have a surface and you have the critical coupling 1/√2 for kappa. Then it turns out that you can do a so-called Bogomolny trick on the energy and see that absolute minimizers actually satisfy a first order equation as opposed to the second order Ginzburg-Landau. They of course solve the second order Ginzburg-Landau equations too, but it can be reduced to a first order one. And these are the equations. The first you can interpret as holomorphicity or anti-holomorphicity, and the other one is what we call in physics, in mathematics, moment map equation. So Bradlow in his thesis showed that when tau is bigger than tau Bradlow, which I will write down later, but it's an explicit quantity, then there are solutions, and if tau equals or less than tau Bradlow, then there are no vortex solutions. So that already tells you that in kappa equals kappa critical, there's a really nice way to interpret absolute minima, but we still don't know about non-minimal solutions. I have to say that these generalize to higher dimensions when your manifold is scalar. Scalar means that it's a complex manifold, so necessarily real dimension even, and there's extra structures too. I don't want to get into that too much. If you know, you know. If you don't, not important right now. So another beautiful result in the theory of solutions on closed manifolds is due to Pigatti and Stern, recent paper where they construct on the trivial bundle non-trivial and non-minimal solutions under the conditions that well, actually, sorry, I shouldn't have that. Forget the second condition. They don't. That's not necessary in their result. I wanted to say that a little bit later. So the condition that they have is that the line bundle is trivial. So there's sort of zero magnetic flux, and that thing about no harmonic vector field. Sorry, that's a typo. He wanted to go somewhere else. So their method is topological. In the sense that they use the fact that the configuration space, so where Nobel and Phi lives, modulo gauge has non-trivial topology. And they also proved that the Ginzburg-Landau energy is gauged Paley-Smale, but they extended this to higher dimensions. And then they had a smart mountain pass argument. So these solutions, because they come from a mountain pass argument, are necessarily unstable, and you can see easily that they're also irreducible. And actually, these are the first examples that are unstable, irreducible solutions on closed manifolds in the gauge situation that I know of. So this is what I mean that by such I mean unstable, irreducible gauge Ginzburg-Landau on a closed Riemannian manifold. So on R2, it cannot happen. Again, it's Taubes' result from the 80s. So on R2, there's only vortices. So the reason they looked at it, I want to mention this quickly because it's very beautiful, is that they used Ginzburg-Landau fields to construct codimension 2 stationary integral subvarieties of manifolds. The idea is that as you look at a degenerating, in some sense, degenerating sequence of Ginzburg-Landau fields, then the zero set of the order parameter in the limit cuts out a codimension 2 subvariety. So I want to get back to dimension 2 because that will catch up with my work. Well, the work was, I think, in either 16 or 17, but it was eventually published in 20, a work of Shishkov, Erkolani, Ryan, and Sigal. They constructed solutions in 2 dimensions using Lyapunov-Schmidt reduction. And I will talk more about their technique and what they proved in the following slides, because this is what Gonçalo and I extended. So let me talk about how Lyapunov-Schmidt reduction can be applied to Ginzburg-Landau equations, and what is Lyapunov-Schmidt reduction. So to begin, we fix a normal phase that is some electromagnetic field that solves Maxwell's equations, and fix your kappa. I'm not going to vary kappa. I'm going to vary tau though, and I'm going to look at the equation as, so one thing you have to know from gauge theory is that every connection looks like your favorite connection plus an imaginary valued one form. So this capital A is an imaginary valued one form. Phi is your order parameter, and tau is the coupling tau from before. So I'm going to call FA phi tau to be the left-hand side of the Ginzburg-Landau equation when you solve for 0. And this nabla in the supercurrent should also be nabla plus 6. So the reason why I'm doing this, well, before I go further, I want to say that if you expand this, you'll see that this equation looks like Laplacian of A in the first term and nabla star nabla minus kappa squared tau in the second component plus lower order terms. It's going to be important later. So it's clear from the definition that when this capital F, this calligraphic F is 0, then we have a solution of Ginzburg-Landau equations and vice versa. And of course, because of that, if I plug in 0 and 0, so A equals 0, phi equals 0, then I get a solution because those just correspond to normal phases. So it would be good, an idea that you can have at this point, motivated by finite dimensional thinking, is that, well, we're at a 0. Let's try to find nearby zeros using the implicit function theorem. The sort of obstruction space where, the directions in which you would be looking for nearby solutions is, if you think about tau as a parameter and A phi as the variables, is of course the kernel of the derivative of F in the A phi direction. Now, this is why I wrote down what the leading terms and the lower order terms are in this calligraphic F, because you'll see that this kernel is the space of harmonic one forms in the first component, and the kernel of this Laplacian minus kappa squared tau in the second component. Now, harmonic one forms are not interesting. They varying in a harmonic one form direction would just change my normal phase, would just change my reference. It's uninteresting. So interesting bifurcation can only happen around points where kappa squared tau is in the spectrum, because when it's not in the, so this nabla star nabla on a closed background is an operator that has discrete only point spectrum, and moreover, every eigenspace is finite dimensional. But the point is that it has discrete spectrum. So I want kappa squared tau to be in the spectrum. So what do I do if I'm in this case? well, let's pick an eigenvalue. And so if kappa squared tau is lambda, then nearby taus, I fixed my kappa, so I only vary tau, will look like, if you solve, actually this factor of 2 should not be there, another typo, I apologize. So it will look like lambda over kappa squared plus epsilon. Now I'm also going to write A as a harmonic one form plus something that's perpendicular to harmonic one forms. And I'm going to write my phi as a capital Phi lambda that's in the lambda eigenspace plus some psi that's perpendicular to that. Okay, so the first terms are always in the obstruction space and the rest is perpendicular to that. And now the idea is that I will split my equation into 2 pieces. Again, I'm not sure why that factor of 2 in front of lambda is everywhere. It should not. But the point is that I first try to solve, or I separately will try to solve f equals 0, the Ginzburg-Landau equations, perpendicular to the obstruction space and in the obstruction space. Now, that's the idea of Lyapunov-Schmidt, is that, under nice conditions, so I have to define what sort of Banach space I'm working on, then I have to prove that f is smooth and in fact Fredholm, its derivatives are Fredholm and so on. But assuming that all the technical details are fine, what I can achieve is that perpendicular to the obstruction space, so perpendicular to the kernel of the derivative, I can do implicit function theorem. So what you can say really is that for small epsilon, so when your tau is close to the bifurcation point, small harmonic deformations and small small perturbation by an eigenvector, there exists a unique B and psi such that, well, I don't yet have, when I use this tau A and phi, I don't yet have a solution of Ginzburg-Landau, but I know that when I plug into the Ginzburg-Landau equation, what I have is living in a finite dimensional space. It's living in this kappa tau, capital K tau. So the only thing I need to solve, as I said, is f parallel being 0. Now the only parameters I have are epsilon. It's a one-dimensional parameter. The harmonic one forms on a compact manifold. It's the first Betti number. That's how many. So in particular, finite number of harmonic one forms, and phi, which is an eigenvector again by the properties of this Laplacian. That's also coming from a finite dimensional space, and I want this to be 0. So the point is that both the unknowns are coming from finite dimensions and the values of this f are living in a finite dimensional space. It's ultimately a highly nonlinear, but a finite dimensional equation. So let me actually come back here for a second. So what Shishka, Verkalani, Ryan, and Sigal did is they solved. They realized that you can solve this in a couple nice situations in 2 dimensions. And what we did with Gonçalo is we pushed it a little further. And I will tell you how we did it. And in the meanwhile, I'll tell you how they did it. So assume now that X is an n-dimensional closed-oriented Riemannian manifold, and either of the following cases hold. Either I want X to have trivial first-Ram cohomology, which is equivalent of there not being harmonic vector fields. This is where I accidentally had that half sentence from originally. And your eigenvalue lambda can be any. Pick your favorite, and there will be a bifurcation there. Or you can have a Kähler manifold, but then lambda has to be the smallest eigenvalue. And this formula I had in the very right is just telling you that you can compute you can actually compute it. It's again coming from a Weizenbach formula. You don't have to think about that if you don't want to. So if you're in either one of these cases, then we can produce solutions through Lyapunov-Schmidt reduction. More concretely, there will be a phi null in the lambda eigenspace of nabla star nabla of unit length, and a corresponding branch of triples, A, phi, and epsilon, that looks like this. So your one form, A, there's a parameter R, which parameterizes the branch. The one form starts out quadratically. The field starts out linearly in the direction of capital phi null, and then there's a cubic correction and lower order terms, and epsilon starts out quadratically. So in every sense of the word, for small r, you're close to a normal phase. And for every small r, this nabla null plus A and phi solves the Ginzburg-Landau equations. For tau, well, not exactly being lambda over kappa squared, but lambda over kappa squared plus epsilon r. So this generalizes the results of Shishkov, Ercolani, Ryan, and Sigal, in the sense that in their case, they looked at two-dimensional closed surfaces, and those are in particular Kähler manifolds. Ours work in larger generality because the dimension can be higher, and in certain cases, you don't have to be Kähler, but then in return, you have to have no de Rham cohomology. And furthermore, what I don't want to bore you with is that this leading order terms in A, phi, and epsilon, they can be explicitly computed in terms of phi null. So how would the proof go? Well, I only need to solve this finite dimensional equation. So remember, this F parallel is the following. I can quickly recap it for you. F was essentially the Ginzburg-Landau equation, right? I just put the Ginzburg-Landau equation, the left-hand sides of the Ginzburg-Landau equation in a vector, and the first component, the second component, and I called it F. And then I argued that parallel to the obstruction space, I can always solve. I can make those components of this capital F 0, and now I only need to make the parts that are parallel to the obstruction space 0. So hypothesis 1 and 2, so either having no de Rham cohomology or being Kähler and lambda being minimal, is to make sure that you don't have to worry about the harmonic one forms. Having no first homology tells you that there are no harmonic one forms, so that's easy. Part 2 is what we learned from the works of I'm just going to say from now Shishkov et al. Is that they realized that when you have a Kähler manifold, so if you just try to do it on an arbitrarily closed Riemannian manifold, you would run into the problem that the harmonic one form that you would need to solve this finite dimensional equation, F parallel equals 0, you cannot make it too small. But if you cannot make it too small, then you cannot do the first step of Lyapunov-Schmidt, or your naive a priori approach would not help to make this A harmonic small. But if you're Kähler and you have the smallest eigenvalue, then smallest eigenvalue of this Laplacian correspond to harmonic sections, basically harmonic functions, and then you can use what's called the Kähler identities and show that the term that would a priori cause problems are actually identically 0. And what we observed is that trick just works on all Kähler manifolds. So we can just forget about the harmonic one forms. And what we have now is, F parallel is really just a function of phi and epsilon. So it's a map from Rn plus 1 to Rn, where n is now the dimension of this eigenspace, which is even because it's really a complex vector space. Now, part 2, and this is where we start to deviate from Shishkov et al. But that they still do that part. They still say that you can pick epsilon depending on phi. You can pick so that phi is going to be perpendicular to F parallel. If you do that, you really eliminate epsilon as a free parameter. You don't have to worry about that anymore. And you know that phi is always perpendicular to F parallel. So another way to look at it, and this is what our idea was, is that this F parallel is really a vector field on Sn-1. Okay, so you can, for every point on the sphere, Sn-1 means the sphere of dimension n-1. So the sphere in Rn, So in every point, pointing to a point in Sn, you have a vector that's perpendicular to that. So it's a tangent vector field. Now, Shushkov et al., their hypothesis that they're formulated geometrically was equivalent to this n being 1. And if n is 1, then S0 is, I know how to, S0 is zero dimensional. Every vector field has zeros. In fact, they're always zero, right? So they were done. And I don't want to act like that this, that was trivial. Getting there was doing much of the work. What we added there is we said that, of course, there's a problem if you just want to argue that this vector field will have zeros in general, because n is even, so n-1 is odd. Vector fields on odd dimensional spheres need not have zeros. But, that's sad. I want to mention that, I wasn't sure how to go on first there. But if you consider this 2D minus 1-dimensional sphere as being the sphere in the complex vector space D, then with a little work, you can show that this descends to CP D minus 1. So there's a U1 action when you look at SD minus 1 as subset of complex vector space. Your vector field going to be equivariant that under that and going to be perpendicular to the orbit. So it descends as a vector field to CP D minus 1. And now we're good. Now Poincaré-Hopf tells us that there's always at least a zero. It would be good to say that this vector field is always zero. That's too much to hope for. But at least we find zeros.
Ákos.
And that proves the existence of yes.
Could you remind?
Yes.
I got lost about this lambda. So where lambda comes from the equation?
Yes. So lambda, if you think about the Kähler case, then it's a minimal eigenvalue, and in the first Theorem cohomology trivial case, it's any eigen value of the Laplacian of a constant curvature connection, and then tau. So this tau parameter, which I think in your paper was mu. I mean, I'm not really using the same.
Yeah.
Lambda is what's in your paper is B. It's the minimal eigenvalue of nabla star nabla, and so at lambda, when kappa squared tau is exactly at lambda,
it enters into the condition in the conditions. That's why I'm puzzled. So what does it mean to have this lambda relation in condition?
Which part are you referring to?
It's condition of the theorem. So you say X has a trivial first Theorem cohomology, and lambda is in the spectrum. So lambda is also related to, so it's combination of the parameters of the equation.
Yeah, so what I'm saying in the first condition is if you have a Riemannian manifold with trivial first homology, then you can pick lambda to be anything. And if you fixed your kappa previously, then the point where the bifurcation will happen, tau is going to be, tau null is going to be lambda over kappa squared.
Okay.
So it means that, you can pick a gigantic eigenvalue lambda,
right,
and, your kappa squared is, say, 7, then I know that there will be a bifurcation when tau is, this lambda over 7.
So lambda, so what I'm saying, that lambda belongs to statement, not to the condition.
Right. Well, yeah, the condition part is that, I wanted to emphasize that in this case, lambda can be anything, but you're right. It's a little bit, it's not phrased well. Sorry about that.
Condition is either X is a trivial first Theorem cohomology or X is a Kähler manifold.
Yes, but in this case, lambda does need to be the minimum. Yes, you're
okay.
yeah.
And in the statement, you specify lambda to be.
Yes.
Okay.
Yeah, you're right. It's a little bit confusing. All right, so this, you know, part 3 proved the existence of the branch. Well, there's a little bit extra work there, but basically have that. Or I think you can see that. And, you know, the rest, by rest I mean, you know, computing explicit formulas for A null, psi null, and epsilon null is more straightforward. So what we conjecture, and is that a lot of things can be improved here. So I don't think that any of this scalarity or trivial first homology business is very essential. I think if we stare at this problem long and work hard, then, you know, we can always deal with the one forms. And I also believe, you know, that's first conjectural thing in this conjecture. The second one I conjecture is that it's not just that for some phenol, you'll have a direction in which you bifurcate. I think you will bifurcate in all directions, all eigendirections. And, you know, the third thing that I conjecture is that the error terms are in fact, you know, not, you know, for example, in the one form part is not small o of r squared, but in fact big O of r to the 4. This is one thing in which Shushkov et al. Actually had a stronger statement, because they did have a big O there, but because of the way in which I'm constructing my branch, I do not have that big O there. I have a small O of r squared instead of big O of r to the 4th, and so on. So that I'm also conjecturing that that will work in general. And, you know, you have such that there's a solution. And of course, this A, psi null, and epsilon should be computed. I should be able to compute. And what's also might be true, and that's even more you know, hopes and dreams, is that these moduli of solutions that bifurcate at those bifurcation points, I expect them to survive. So if you want to, you know, when lambda, or sorry, tau gets bigger and bigger. So what I mean is that the moduli space of all Ginzburg-Landau fields modulo gauge should be the union of this, so let's call it x lambda tau, where x lambda tau is this space of solutions that bifurcated where we pass the eigenvalue lambda. Of course, I'm not saying that they will be, you know, this is a very vague statement. I'm not saying that, you know, the fields don't change, but as a family, they survive as a critical set of the functional. I have a reason to hope for that, other than that it would be a pretty statement to prove. And I will tell you in the previous, in the next slide, why I hope that. But, you know, I don't have a very good idea how to prove that sort of statement just yet. I would be just happy if that was true. And to finish, I want to make a couple of remarks. So as I said, our error terms were weaker than that of Shishkov et al., but we hope to improve them. What I didn't emphasize is that the zeros of that vector field, they don't just give you solutions, they classify all solutions. So you have a nearby solution if and only if you have a zero of that vector field. And what my expectation is that nearby, you know, it's not just branches that bifurcate off, but full families of moduli. So in other words, I expect that vector field not just to have zeros, but to be identically zero on the projective, complex projective space. Again, it's conjectural. Hopefully we'll be able to improve our result to that. And as I said, I don't expect those hypotheses on the underlying space to be very crucial. So one direction in which I could, I think, generalize, but I haven't given too much thought of that, is at least surfaces of constant Gauss curvature, because in those cases, there's very nice explicit formulae for for these eigensections. And this is a very, very nice paper of Olmoro and Prieto, if I'm pronouncing the names even remotely closely well, who wrote down these eigensections. So that might be a good direction. What we also proved in the paper, unfortunately, I didn't have time to talk about, is that the existence of non-minimal solutions in 2 dimensions, though, for arbitrary or more generic kappa and tau, not just near an eigenvalue, that use the topology of the configuration space in a way. And we also proved instability of non-vortex solutions. But again, I didn't have time to talk about that too much. A related direction that we might also pursue is proving Morse index and nullity estimates for these non-minimal solutions. So how much the energy function will look like a Morse bot function around a critical value. That's a reasonable question to ask. And there was some related work that was motivational to us by Kelleher, Gursky, and Streets. And we want to recruit Casey Kelleher to work on this problem with us. But that might be a direction where we go. And I want to once more talk about the work of Pigatti and Stern. So they had this theorem that helps you extract codimension to minimal, integral, stationary, blah, blah, subvarieties out of degenerating Ginzburg Landau fields. And this is one reason to wish for a theorem like the one on the previous slide, to wish that the solutions that we construct survive. Because if we can also show some energy bounds on them, then this result of Pigatti and Stern would immediately apply and would allow us to prove existence of these minimal subvarieties, but such subvarieties that are non-trivial in homology, which Pigatti and Stern couldn't do. But that's all for today. Thank you for your attention.
Thank you very much. Beautiful talk. So do we have questions for Ákos?
I have a couple of questions.
Yes.
So you mentioned that Taubes proved that there's this higher non-minimal solutions in R2.
Yes.
But there are vortex lattices in R2.
Yes. So
kind of energy.
Yes. So Taubes' theorem really says that you don't have finite energy.
Finite energy. That's
other solutions. If you define your energy functional as the integral, so this energy density that I had makes perfect sense on any background. And if you define your configurations that you want to look at as having finite energy on R2, then what he proved is that, well, then the only solutions are vortices. But you're absolutely right. I was a little vague there. There's of course vortex lattices, and there could be infinite energy non-vortex solutions.
Right. And again, the Taubes work was only for the critical kappa, right?
Yes, vortex equations only make sense for critical coupling.
Only for,
yes.
He did only for critical kappa.
Yes, and I should say that the Pigatti-Stern business also uses exactly the critical coupling because they want to have vortices lying around. So this is why I mentioned this at the same spot.
Right. So what happens if you assume your kappa approaches critical value?
You mean in R2 or?
Well, no, on your
theorems?
In your setup, but what happens at the critical? Did you look at your results at the critical kappa?
We don't get anything extra out of that in our analysis, interestingly. Kappa factors in, for example, one interesting thing that I didn't talk about, but now I mention is that this epsilon null when you're in case 2, so when you're looking at a Kähler manifold and the lowest eigenvalue, that epsilon null is positive. But depending on kappa square and the eigenvalue in case 1, this epsilon null might be negative. So it could happen that at birth, but it can also happen a priori, although I couldn't prove that actually it happens, is that as you pass that eigenvalue, the topology changes because solutions come there to die.
Mhm.
So there's that sort of weird things that happen in terms of, when you change kappa, but there's nothing qualitatively different happening, vis-a-vis the proof of the theorem as it is right now.
Mhm.
But yeah, it surprised me too, but it's true.
Okay. So you're using more robust techniques which work in both cases, and that's
yeah. So. And I'm also getting less. Maybe I'm not getting the full detail, because all I'm saying is that, well, yeah, solutions there will be solutions nearby, but I'm not saying too much about their form or properties, or definitely not saying anything about the physics. I wish I was able.
But also for critical cases used for topology specification for the yeah. Four manifolds. Okay.
Sorry, I was muted. Are there other questions for the speaker?
Yeah, Ákos?
Yes?
I'm sorry, so somehow my internet was not working all the time, so maybe you've answered that, but so you construct local curves of solutions, if I understand well. Do you know if you can extend them all the way? Like,
oh no, these are solutions on the full manifold.
But they are parameterized by R, no?
R is just, it's R, so no, R is not, maybe I shouldn't have used R. R is not sort of radius or anything. R just the branching parameter. So at R equals 0, all these parameters, A, phi, and epsilon are 0, and you just have nabla null 0, you just have your starting Maxwell solution. And R is just tells you how far away you branched off. It's not a radius or anything. They are global solutions on the full, curve or manifold, or they extend everywhere.
No, but I think the question is if they exist until tau reaches infinity for all tau.
What?
Yeah.
No, no. So this relates to this very wishful conjecture at the end that, I know that this family exists because it's an implicit function theorem argument. Ultimately, these exist for some small r, and after that, I don't know what happens to these solutions. So you cannot make R too large either. But for small r, maybe it's like 1 over a trillion. But from 0 to a trillion, you can from 0 to 1 over a trillion, you can put in every r, and you'll get a solution whose leading order terms will look like this. That's the claim.
But then, for example, in case 1, you construct several curves because you have one for every lambda, if I understand well. Do you know that those curves are different?
So for different lambdas, I construct different families. That's true.
But could it be that they're in fact all part of a bigger curve of solutions?
Yeah, that could happen. That could happen. I do not know that because it only, I can only show that there's a legit bifurcation there, but I don't have yet a mean to a way to show that what happens with that family once you reach R null or beyond.
Yeah, thanks.
But thanks. I was happy about this statement because I was interested in whether there are solutions on, say, a non-trivial line bundle that are not vortices or absolute minima. And then Pigatti and Stern's result me more motivated. And now we know that not on every manifold, but on a lot of manifolds, there are definitely infinitely many such solutions.
So why do you say they're not vortices?
Because if you're sorry, in case 2, you can have kappa naught 0. So they're not vortices in the kappa naught 1/√2. So you can have non-vortices in this strict sense that they're not solving the vortex equations as I define them. But in case 2, you're right, they're still absolute minima that we're constructing. But in case 1, if you pick a big lambda, then the energy will be ordo lambda squared. So you can easily see that those are not the absolute minima.
No, but how did you find a vortex?
Well, as I said, the way I defined in this talk is by the vortex equations. But if you want to define them as the absolute minima in 2 dimensions, even then, where was I? Actually, probably easier if I go to the.
I would define a vortex as a solution with non-zero degree.
Yeah, well, then they are vortices, of course.
Then they are vortices, because degree tells you that.
They're of course. Yeah, they're going to be a generic section of this line bundle. So, for example, on a surface, you of course will have a couple zeros and potentially anti-zeros, and that in that sense they are vortices. I call the vortex something that solves. Where was it? Solves what we call the vortex equations. But physically, I know that that's not.
Yes. So. I mean, the vortex in a bathtub is a vortex, and it doesn't solve any. When you pull a plug in a bathtub, you have a vortex, and it doesn't solve this equation. So vortex is defined by degrees, but the fact that you have a vorticity, right? That your supercurrent goes around the zero.
Yeah, in that sense, they are vortices. Yes.
Can you say anything about zeros of these solutions?
No, we haven't looked at that question yet, but it's a good question. But we haven't studied that.
All right. So do we have other questions? Otherwise, we can continue our discussion offline. Maybe thank the speaker once more. Thank you, Ákos.
Thank you so much. Thank you.